So, welcome to the next module. We are now entering to the module 9. It is the second last module. So, we have covered so far the top 8 modules in the systems engineering and applications course. So, in this particular module, we are going to see that what are the systems life cycle models. We have studied systems in detail. We understood the foundations and concepts, mathematical expressions, optimizations, conceptualization techniques, brainstorming, and many other things we have studied so far. And along with that, in last few modules we have studied the application part, that what is models, what are the type of models, right? And what are the modeling techniques, what is RFLP, what is MBSE. So now we are going to understand, okay, fine, there are several ways to express the models. What is the life cycle of the systems, right? What kind of those models or what kind of those guidelines we use in the to understand the or to develop the systems. So different kind of life cycle may be required to develop a system depending on the system context, right? So you, as you see, we are now in the module 9, where I'll be expressing the thoughts on this particular module 9. So systems life cycle. So systems life cycle basically indicates the sets of activities and their arrangements in such a way so as to optimize the time, efforts, and systems performance in order to come up with an effective system outcome, right? So in the systems life cycle, we have to define the arrangements, how we are planning everything, how we'll be executing the whole thing in the systems life cycle, so that in smaller span of time or smaller investment, we can come up with the systems plan properly. So that we'll be going to see in the systems life cycle. During the life cycle of any system, it requires methods, tools, processes, and resources, which may vary from task to task. So, this during the life cycle, it is basically the a method to perform a task and provides how to perform each task, right? Life cycle is used to basically describe the changes or changes in the changes, or you can say the changes in the stages that a system goes through. That this is the first phase, then the second stage, then the third stage, then the finally now the system is finished, closed. Not only this, it basically helps to conceptualize the system, that in what sequence the events will take place, and what will come first and what comes after that, and what is the style of arranging. That is why the different life cycle model exists, and which may the implementation of those models may vary depending on the context of the system or the context of the product. Depending on that, we may adapt different kind of life cycle model. So we can think of systems as entities that are conceptualized, produced, utilized for different purposes, right? Many times we just focus on the development phase, right? And then we talk about the system or product development life cycle. So the system life cycle is related to define that how the tasks will be one by one, how the tasks will be sequenced, and how what is the process of managing the system basically. And that may vary depending on the context. So here you can see that there exist different arrangements of tasks and processes in the form of models to achieve the desired work. They're depending on the categories of the systems. The four commonly known models are expressed. One is waterfall model, another is the walking skeleton model, third is the spiral model, and fourth is the V model. This is the in conclusion, these four exist, but in different you might have heard about a spiral model in context of software, life cycle development model. Then you might have heard about V model for development of prototypes in the manufacturing domains. Then you might have heard about waterfall models in the project management modules. Then walking skeleton is something, just the initial phases of the products or processes, right? So this is how, these models can be utilized in different contexts depending on the requirements, right? So first I'll be talking about the walking skeleton model. What does it mean? Very basic but very important portion of the final system design. For example, if I would like to design a car, let us say, to use the walking skeleton model, how will I do, how will I process my system? How will I develop the system? I will say I will first develop the requirements, the basic skeleton. I will be saying the skeleton would be an engine attached to a chassis or with wheels, right? And then when the basic step will done, then I'll say, okay, now I'll think about the external structure, then I'll think about the seats, then I'll think about the electric wiring, and then I'll be thinking about some more more and more features to reach out to the final process, right? So in the walking skeleton model, we keep on adding feature by feature, right? Feature by slowly we'll be keep evolving with the adding the system components one by one. So in this, what will happen, when at very first stage we create the basic outline of a system, then then we keep on adding the features. Initially we added engine, then we added some chassis, then we added some wheels, then we added some seats, then we added some external structure of the car, the design and other things. So we keep on adding more and more and more features. So in the skeleton, we started with a blank two features, then we keep on adding more and more and more feature, and then the whole car will be, or whole four wheeler will be developed, and at the end you will get the final system, the final vision of the system you can see in such steps. So it's a kind of walking skeleton model. The name itself suggests the details are missed out, the functionalities of the system is less focused, the more focus is upon on the features of the system. How will we keep on adding the feature, though the logics is maintained, because logically they are building up or adding up more and more features. The requirements they are considering, based on the requirements and logics and the functionalities, they are keep adding on more and more features. But this is the less insightful process or less insightful life cycle model of a system. So for the less complex projects or less complex systems, we usually use this kind of walking skeleton model. Then the next is waterfall model. Waterfall model is commonly known in the domain of project management, right? Waterfall model says that you should decide everything in advance. It's a plan driven kind of systems. When you planned everything in advance, you know that what exactly you are going to do, what is the logic, what how exactly you are going to feature it. You are very clear with your things. The sequential or flow down approach, this indicates, the term itself indicates, the flow down means the change, or you can say the change resistant models. When you are changing something, it will not be easy to adapt that change, right? So the systems requirement, first you have to mention the systems requirement in very much detail. Then the next is the designing and planning. Once you define the systems requirement properly, then you go to the next phase of the systems life cycle. The next phase will be designing and planning. It the downside arrow itself indicates that once you define the system's requirement, further you have to design and plan. There is no arrow going back here, mind it. Everything is towards downside, down flow down approach it is. Then once you completed the designing and planning of the system, you have to plan for the production and manufacturing depending on the work or the context. Then you have to go for the testing or quality checks. Then you say that now the system is ready and it is in operations. After that, once its operational life is over, then it will be retired or it will become obsolete. Okay, fine. You see, it is all flow down approach, sequential, one by one things will be happening. The change is, the possibility of change is very less. You have to finish the things properly in the first phase, then only you will be able to move the second phase. So one more, term is there these days, concurrent to collaborative engineering. So the concurrency and the collaborative engineering terms are missing here. It's a sequential approach. How? Because all these changes which are suggested in the first phase or first stage or second stage, third stage can happen and can lead towards the end of the life phase. So everything is getting connected with this particular standing line in the flow chart or in the model. So this is how one by one things will be happening. If something happens in this particular phase, you have to go back once again to the previous stage. You have to reiterate the whole process, right? Then only you will be able to change anything in your life cycle model. So this is how the processes on the system's life cycle may be fulfilled. Then the spiral model, right? In the spiral model, if you closely see, the very important thing is requirements development. Very first phase is spiral model. If you closely see, what is the difference between this and this? Here things are flow down approach. One by one things are happening and one part is completed as a whole. Systems requirement at one point of time, all the possible requirements will be completed in this phase. But in the case of a spiral model, what is happening? You see the arrow from the inside arrow. When this particular, you see this model is the lines, the spirals are starting from this particular point. The innermost spiral is starting from this point with the small set of requirements. Then you develop that small set of requirement, plan and design the system. Then the system configuration will be prepared. Then in the next step, the testing and evaluation of those small set of features will be done. Then the development will be done for that particular small set of requirements or features. Once finished, then it's a small incremental development of the system. Then the next requirements will be developed in this particular phase, right? And then we will be keep on doing the planning and designing for the additional requirements. So this is how the next phase will be completed. That will be the systems configuration. So you see the 5 phases will be keep on repetitive. Some features, some requirements, finish the 5 phases, then reach out to the next requirements will be add on, finish the requirements development, plan, design, prepare the configuration, test, evaluate and develop. Like this whole iterative spiral cycle will be keep moving on, and a point will come when you say that all the systems requirements have been fulfilled. So you see that there is a spiral model is basically indicating the life cycle for different requirements. As the time is moving, more and more requirements are getting developed, and all will be implemented in the integral way. Or you can say it's a piecemeal delivery of the system, or the piecemeal no, the development of the systems. One requirement completed, second requirement completed, third requirement completed, whole life cycle phase. This is how the final life cycle, final system will be visible to you. Okay, so in the spiral model, this, this step by step approach is very useful these days. The way we are in the, the customer is very important, the stakeholders are becoming very important these days. The requirements generated are need to be, no, need to be fulfilled, but how will you fulfill if you do not understand the things clearly? So it's, you can say it's a kind of agile kind of structure. Agile in the sense, huge possibility to adapt the changes. Agile name itself defines that this particular life cycle model indicates that whatever changes in the requirements can be easily adapted through a different spiral. While in the case of, if you go back and you see the waterfall model, all the systems requirement must be completed in this first phase. Then only the whole complete designing and planning will be started. While in the case of a spiral model, one by one requirements are coming up, and then before that particular requirements, planning, designing, system configuration and other things are slowly getting developed. So that is more change adaptive. It is very difficult to jot down all the requirements at a single phase these days in the such a technologically unstable domain, right? Then the most important and useful model in the in the case of engineered systems, that is called the V model. Though verification and validation is something which is required everywhere, whatever system you are developing, you need to verify and validate. Because if you remember the four attributes, the target is where one of the attribute of the system. So when you have to meet a target, you have to verify and validate each time with the stakeholder whether whatever you have developed, is it all okay, it is all aligned with the scope, it is all aligned with the target, then only you move on, right? So verification and validation is the basic component in each systems. But this verification and validation model, the V shape itself expresses a lot of things. What is the difference here? In the V model, there are two edges of V. On the left edge of the V expresses the conceptualization of the physical designs, right? And the right hand side is right edge of this V basically is verifying and validating each progress step. So now the question is, what are the progress steps here? So progress steps. Now the question is, what do you mean by verification and validation? So validation is something, will the system meet customer needs? Whatever I've developed, will it be meeting the customer stakeholders requirement? Am I doing right or not? That is called the validation. The second term mentioned here is verification. What do you mean by verification? Verification is basically, will the system meet the technical requirements? Have I jotted down all the requirements which you mentioned in the functionality list? So we are so one is, are we building right or are we doing right? And the thing is, are we building the right thing outcome is all clear, whatever you were intended to, will the system is going to fulfill that particular desire or requirement, yes or no. So that verification, whatever is there, whatever you wanted, everything is listed down, everything is, all the functionalities are mentioned, yes or no, that is called the verification. Then the validation part says, whatever, based on all these mentioned functionalities, will this system be performing the way we wanted? So that verification and validation is something which we have to keep on monitoring all the time, right? So one side in the V, left edge and the right edge, these two edges are actually expressing all the all the required work and how we will be moving in this system's life cycle, how we will be putting the verification and validation in our system's life cycle. A manufacturing system and a software system. What is the difference between these two systems? You see, when I talk about systems, it means some requirements is there of the particular manufacturing system and the particular software system. This, in this systems engineering, we are not distinguishing between these two systems. We are just developing the life cycle phases. How do we manage, how do we come up with the right requirements, right functionalities, and how do we plan the logics, and how we will be developing the final designs for developing the prototype, right? Or maybe the final product, right? So that we will be discussing in this particular course. So with this V model, we will be discussing about the those two different the systems. So here, if you see the V model, this V model clearly gives a framework that how the system should be developed. Because if you develop, or if you mention all the requirements, if you forget to verify and validate, can you be saying it is a complete systems process, complete systems life cycle? No. It requires, it's a mandatory requirement of verification and validation throughout the systems life cycle, right? So this model helps us to improve the transparency, better communication with the stakeholder, right? And the most important thing is it minimizes the risk. You develop something and you keep on verifying and validating with the stakeholder, whomsoever. So it minimizes the risk involved in the whole system development, right? So that is one angle. And definitely when you keep on verifying and validating the requirements, the functionality, the operability, everything you are keep on verifying, so then it will be, the development time, there will be no rework, the cost will be lesser, everything you know in advance, all things are approved and agreed on. So this will become very easy to carry on with the final production, right? So that is why the V model is the most favorite model among all. Though the spiral model itself is very important, but that utilization of the spiral model is in the software domains, where we know the software features, and the features are keep adding on, the requirements are keep adding on, and what will happen that we'll, whatever features we're having today in our hand, we'll complete that particular piecemeal and we'll be keep on delivering in pieces. After that, we'll more improve the code, the next feature will be developed, and that is why the whole complete software or complete website can be developed, right? So the spiral model is more common in the software industry. Most people utilize it. The waterfall model is usually utilized by the in the traditional systems, right? Very where things are almost fixed, and when people are practicing it since long, very few chances of changes, and things are happening in the standard mode. No, not much innovation is possible, and this mechanical system is moving on the way production of sugar production system. machines are aligned in such a way, and then very low complexity, very less complexity. So the least complex systems can follow the waterfall or the skeleton, walking skeleton models. So these two models are basically applied in the domains where the complexity is very low. Standardized system is followed in the systems. But the this spiral model, as I already told, in the software domains is very popular, and V model is very popular in the manufacturing systems. So this was a difference which I wanted to discuss here in this session. That when you talk about difference between software systems and manufacturing systems, so this is the difference, because the context of the target is different in these two systems. For software systems, the target is the systems should be functioning. It's an intangible thing. But the tangible product, manufacturing something, when the product has to perform, or you have to manufacture a robot or a particular machine, right? And it should function in that way. So the complexity is little higher in manufacturing system than the software systems. That is the reason why the verification and validation is more important, though it is important everywhere. I already explained it why. But in the case of manufacturing systems, it is more having more importance. Why? Because when you develop some, in manufacture some cut some components and you develop some shape, some tangible products, so the reworks will be very, very difficult. The risk will be very, very high if you do not verify and validate properly with your stakeholder. Let us say you wanted to develop, you wanted to create a bottle of 1.5 liters, right? But you created a bottle that is just 100 or 150 ml less in capacity, and now your stakeholder is saying now it won't work. What will you do? You have to scrap your manufactured product. So the risk is very, very high when you are manufacturing some products. So hence the verification and validation is more focused in the manufacturing systems. So with V model, I am now going to introduce you again I am reconnecting this models that how we will follow in the case of engineered systems. So in this particular session, I am more focused on the engineered systems, though the softwares are also the engineered systems, but I am more focused on the tangible product development, or you can say the product development processes, and the uh, the manufacturing more, right? So the RFLP approach, which we have just seen few minutes back, remember, now I'm going to replicate. Remember, now you see, you have seen the V model. Left edge, we have seen that it's a conceptualization to physical design. One by one steps we'll be taking. We'll be coming from starting towards down, and then in the right edge also we are coming from starting to down, and then we are creating a V-shape model. The main takeaway or main logic is to verify and validation model, and which is required to be done every time. Now I am comparing this V model to the RFLP approach of MBSE modeling. How we utilize this V model for development of the systems life cycle in the case of manufacturing systems. You see, R was represented by the conceptualization of stakeholders requirement, right? And then the moment you are capturing the requirements, you have to get it validated. You have to get it verified for its feasibility and alignment. That is the one phase R. R is not just understanding the requirements or jotting the requirements down on the document. No, it is to verify, to check the alignment also with the stakeholders' agendas or goals. After the requirements development, we go for with the F phase. F is the defining the system's requirement. What should be required in the system? What is the functionality? Then these systems function will be required to verify and validate it. In the next phase, L phase, it is detailed designing. What are the logics among these particular components and functionalities which we have mentioned? Then for this L, again we will be keep on verifying by integrating and testing each components whether the functionalities are met or not, whether this component is able to perform or not. The functionalities which we were looking forward for, are they logically connected and able to perform or not? Then in the P phase, we talk about the physical components. Physical means the components, the design, or it may be the real component, right? And then we'll be again doing the same thing, the components testing. The components testing will be done, and after that we will be saying that after doing this RFLP or following the systems life cycle model. You see the V is there. I hope you all are able to see this V. Now the base of V is systems implementation and development is now done. So once you complete all the phases R, F, L and P, then only you will be concluding that now my system is developed and implemented, right? All the phases are properly done. Verification and validation we were keep on doing in all the phases, R phase, F phase, L phase and P phase, right? So this, the requirements, functional, logical and physical framework is actually utilizing the V life cycle model of a system, right? So in this, the requirements domain captures the objectives, all the constraints which are required to be fulfilled in a system, right? Or basically you can say based on the stakeholders perspective, we develop the requirements. In the F phase, we define the functionality of the system, right? That what kind of functionality is required to be there in the system, or the capabilities to be achieved. Then the L phase, the logical domain, which shows how the system operates logically, right? Through the functional connections. When you connect all these things functionally, all the functions are connected, then how the how these systems will perform together, how will they logically behave in the for the physical development. And the last phase, the P phase, physical domain, involves the creation of the systems. It may be hardware, software, or maybe other physical components which are associated together. So after performing all these things logically or properly, we will coming up to the final deployment of the system, right? And this is how we'll be able to complete. So that is defined here in this RFLP approach. The same thing which we have mentioned here, the same thing has been developed, that how the system goes on. So you can say this RFLP is the major foundation of MBSE, where we include the V model and we come up with the systems implementation framework. So this RFLP model, I think most of the things I've already explained, right? So requirements, functionality, logical and physical is already explained. So now the very important question comes up here is that all fine, theory is all good. What is the application part? So I am taking you to the application part, the modeling languages. If you remember the introduction, lecture, where I already covered this, sysml models, what kind of sysml diagrams are there. So again, I am repeating the same thing. Sysml is basically a general purpose modeling, as I already explained. It helps you to specify, to analyze, design, verify, and validate the particular system or a system of systems, right? So it's a commonly common language, and then it has been developed by the Incose. The three basic diagrams we use in this MBSE modeling, that is requirements diagram, structure diagrams, and behavior diagrams. So now the nine, all this sysml modelings, actually the foundation of the sysml models, basically they express the nine kinds of diagrams, in which four kind of diagrams express the structural features of the components or systems. Then four diagrams are there which express the dynamic behavior of the system or components. And then there is one separate diagram that is called requirements diagram, right? Is if you see what are the four types of structural diagrams: the block function definition diagram, internal block diagram, package diagram, and parametric diagrams. These four types of block diagrams are used to define the structural requirements of a system. Then the next four are under the category of dynamic diagrams, which requires to express the dynamics or the logics and the functionality of the system's features. Activity diagram, sequence diagram, state machine diagram, and the use case diagrams. And the last, the ninth one, which is the requirements diagram, right? So this is how this nine SysML models we'll be using in next stage. So okay, fine. I mean, some of the students were asking me that which kind of softwares do we use. So to introduce the list of softwares, there are several softwares in the market these days. So some of them I'll be discussing here. That one is the Cameo Systems Modeler, which is also a very good tool of SysML based modeling, which is developed by Dassault Systems. Dassault is a French company. Then the second is Capella, which is one of my favorite. So why Capella is favorite? Because it's open source MBSE tool. Thales Group has developed this Capella software. As you know that we are developing the systems requirements in a logical way, so that the architecture is developed, and now it is ready to to manufacture, and you can say the production, right? So up to that point we do everything so well, we design every system so well. And to design the systems, it is very much important that whatever architecture you have developed, it should be integrated with your manufacturing systems, right? Or with your design portals, so that you can understand, you will be able to keep on verifying and validating the systems requirement while you are doing the manufacturing and the real time operations. Okay, so the integration and interoperability of this modeling software is very required to be there with the other manufacturing setups or designing setups, right? So the Capella is one of the open source software which is very good, having very good integrability with other softwares. Then the next software is Enterprise Architect, and then the next is Rhapsody, is also one of the softwares for the SysML tool, which has been developed by IBM, I think. Then Dassault has developed two interfaces. One is Magic Draw and another is Cameo, right? Cameo and Magic Draw has been developed by the Dassault Systems, a French firm, and these software also do very well with the complex systems. Though these are the particular softwares dedicated to SysML modeling only, but our traditional softwares like MATLAB, Simulink, system composer, requirements toolbox for MBSE you can utilize in MATLAB, and that also works so well, right? So I have worked on two softwares very closely. One is MATLAB and another is Capella.